Okay, we will start now. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL-PMRF Teaching Assistant for the course Probability and Statistics. This course is offered by Professor Somesh Kumar. He is a faculty in IIT Kharagpur. So this is the 8th week live session for a course which is of 12 weeks. You people have already known these things. Okay, so probably this is the last week for the probability course. Okay, from ninth week onward, we will discuss about statistics more as compared to probability. Okay, so in this week, we will mainly discuss about the first topic is sampling distribution. Okay, in this like small sampling distributions are like T, F, and chi-square. Okay, these three are like small sampling distribution, and we will discuss these three. And if you may remember, you may find out we have learned about the chi-square in the 7th week as well. Okay, so we will start from there. Before that, what is the meaning of sampling distribution? Okay, so like as we know, we have parameters. Okay, and we have random variables. These are already discussed. So parameters like function of population values, like population mean, population median, etc. Okay. Then as an alternative of these parameters, we use statistic. Statistic is like functional functions of sample values. Okay, so we will discuss more about statistics in the ninth week onward, but these are like functions of sample values. Okay, so that is sample mean, sample median, sample mode, sample variance, etc. These are like drawn from the samples that we have randomly drawn from a population. Okay, so these are called statistics. Okay, since these are actually values of the random samples, random variables. So that's why it also follows some kind of distribution, like sample mean x bar, okay, sample median, sample mode, or variance, anything like these are the functions of sample values, and these are uh, like uh, these are used, these are also follows some kind of distribution. So out of those there are three small sampling distribution, that is T, F, and chi-square. Okay, so we will discuss about these distributions. So let's start with chi-square distribution. So chi-square distribution is like suppose we have a random variable, suppose W, which follows chi-square distribution with n degree of freedom. Like in the previous distributions, we have parameters. Here, the parameter is like termed as degree of freedom, and here n, there is only single parameter, that is single degree of this, that is called degree of freedom. Okay, so W is a random variable which follows chi-square distribution with n degree of freedom. Okay, then the probability density function for this W is like this. It's 1 upon, it's 2 to the power n by 2, gamma n by 2, and then it's e to the power minus W, W by 2, and w to the power n by 2 minus 1. W is greater than 0, n is greater than 0. Okay, so this is the probability density function for the chi-square variant. Okay, also you may find some resemblance of this W variant with some other well-known distribution, and that is the gamma distribution. Okay, for some specific parameter value. So this is nothing like here we can see that W follows the chi-square distribution with n degree of freedom, which is a special case for gamma distribution with the parameter values like n by 2 and 1 by 2. We have already discussed many times that most of the distribution, or we can say each and every distributions are correlated or transformed with another distribution via some transformation method. Okay, so or some particular values. So here like chi-square gamma distribution for this value becomes chi-square distribution. Okay, so this is the PDF. Now we have PDF. Its CDF is not well defined, as we already know for the gamma variant as well. We found the same case. So what is its expected value? Okay, we need to find the description of the distribution. The description means mean, variance, skewness, and kurtosis. Mainly these four things. Okay, so like expected value of the chi-square variance. So it is nothing but the degree of freedom itself. Okay, so expected value of W is the degree of freedom is n here, so it's n. Now its variance. Variance is like twice of the degree of freedom. That means the variance of a chi-square variant is always greater as compared to the mean value. Okay, and then we have skewness and kurtosis. Obviously, for skewness we need third, and for kurtosis we need fourth central order moment. So the third central order moment for the chi-square distribution, that is mu3, is actually 8n, okay, which is already greater than 0. And the fourth one is like it's 12n n plus 4. Okay. Now, if you may remember, you may find that the coefficient of skewness, that is beta 1, which is mu3 square upon mu2 cube. You may solve and found out that it comes out to be 8 by n actually. Okay, 8 by n. So, so this is always greater than 0. So this implies the beta, sorry, the skewness, the coefficient of skewness is always greater than 0, implies positively skewed. Okay. For large value of n, it comes out to be 0. That means for larger value of n, it becomes like from highly skewed to slightly less skewed to symmetric. Okay. Now the next is beta 2. So beta 2 is like mu 4 upon mu 2 square. So mu 4 value is this and mu 2 square is 2n. So after solving, you may find it 12 upon n, okay, which is already greater than 0, always. Okay, so this is leptokurtic. So leptokurtic means peaked as compared to the normal distribution. That is peaked as compared to normal curve. Okay, so that is leptokurtic, positively skewed, and the mean and variance are given there. Okay, mean is always less than the variance. So this is the chi-square distribution. Similarly, we have more distributions, like the second one is T distribution. So the T distribution is like, this is also called like student's T distribution. students T distribution. Okay, so this can be derived since it is a transformed kind of variate. Okay, so suppose x is a random variable which follows normal 0, 1. Okay, and y is another random variable which follows chi-square distribution with n degree of freedom. Okay, now we transform a random variable t, which is defined as like x divided by the y variate, that is the chi-square variate, the chi-square variate divided by its degree of freedom n. So this is a transformed random variable, and this transformed random variable follows t distribution with n degree of freedom. Here also, the parameter is n, the degree of freedom itself. Okay. Now we define how the t distribution is defined. Now the next step is to find the PDF, the density function for the t distribution. Okay. So the density function will be like 1 upon root n, and then its beta function, it's n by 2, it's 1 by 2. Okay.
అయితే నా దగ్గర
Uh,
చార్జర్ పెట్టు నా దగ్గర ఉంటుంది కదా
just give me a minute.
చార్జర్ ఉంది కదే
Yes. So it is like the PDF will be like 1 upon under root n, the beta function with the parameter n by 2, 1 by 2. And then it's 1 plus t square by n. This is the probability density function for the t distribution. Okay. So obviously its CDF is again not in closed integral form. Okay. So this is the case. Okay, there is one thing I think I have written wrong. The thing is, it values comes from n, minus infinity to n. Okay. Now there are some property related to this t distribution actually. Okay, the first one is like it is symmetrical about t equal to 0. Okay, the thing is that this distribution is symmetrical about t equal to 0 in the same manner as the standard normal variate is symmetrical about z equal to 0. Okay, so obviously that means its skewness comes out to be 0 and it is symmetric in nature, that we will solve. Okay, now the next is its odd order central moment, that is suppose 2k plus 1 comes out to be 0 for all k equal to 0, 1, 2, and so on. Okay, the it's symmetrical about t equal to 0. Its odd order central moment comes out to be 0. Okay, and then since its odd order comes out to be 0, its expected value also comes out to be 0. Okay, now its variance. The variance of this is like n upon n minus 2. So obviously, this simply means the numerator is greater as compared to the denominator, and the denominator is smaller. So always greater than 1. Okay, it's always greater than n upon n minus 2 comes out to be more than, or for large n approaches to 1. Okay, here n is greater than 2 actually. This is the case. Okay, now the next thing is it's skewness. Skewness, what is skewness? We need to omega of like mu3, which is comes out to be 0 as the odd order central moment comes out to be 0. The mu4 is also there. The mu4 is 3n square, and it's divided by n minus 2. n minus 4 or n is greater than 4. Okay, so these are the third and fourth order central moment. So yes, it's beta 1 comes out to be, the numerator comes out 0. So it's 0. That means symmetrical in nature. Okay, so the t distribution is symmetrical in nature and the point of symmetricity is t equal to 0. As same in the case of standard normal variant. Okay, now the beta 2 is like 6 upon n minus 4. Obviously, for n is greater than 4. Okay, so you may find out it's more than 0 actually. Okay, it's more than 0. So this implies it's leptocotic as well. Okay, so that means what? The curve has same kind of structure as standard normal variate or standard normal distribution, but just a little bit peaked as compared to the normal variate. Okay. Even you may find out in future that for large N, for more than 30, the T table and the normal table are same. Okay. You may found this thing as well, that when we solve some numericals based on the T distribution, then you may find for large N or large degree of freedom related to the T distribution, we will see the normal table as instead of the T table. Okay. So this is the T distribution. Now the next is F distribution. Now the F distribution is like, again, it is also one of the sampling distribution. So suppose we have Y1, one distribution, sorry, one random variable Y1, which follows chi-square distribution with m degree of freedom. The second Y2 random variable, which follows the chi-square distribution with n degree of freedom. Okay, then we define a or we transform the random variable u, which is defined as the like it's y1 divided by m and ratio by y2 divided by n. Okay, so that means the chi-square variate divided by their degree of freedom, and then the ratio of those two chi-square variate with divided by their corresponding degree of freedom. This new random variate is nothing but the f variate, and the distribution followed by the known as F distribution with the degree of freedom. Here again, the degree of freedom word is used. The degree of freedom or the parameter you may say M and N. The numerator will be like M and the denominator will be like N. So M N. So this is the uh, definition of the F variate. Okay. So yes, we need to find the probability density function for this F variate, which is like m by n to the power n by 2, 1 upon its beta function n by 2 n by 2. Then it is like u to the power m by 2 minus 1, and the denominator is like 1 plus u to the power m plus u multiplied by ml whole to the power m plus n by where u is greater than 0. So this is the density function for the F distribution. It may looks like some kind of beta distribution, not exactly, but some kind. Okay. This u term, the numerator u to the power and the denominator 1 plus u to the power terms are there in the beta distribution as well. Okay. So this is the case. Now the next step is to describe with their mean variance and all. So it's expected value is like n upon n minus 2. So that means it only defined via the second chi-square variant, the degree from the second chi-square variant. Okay, no matter what will be the degree of freedom for the first variant. So it's n upon n minus 2. Again, it is always greater than 1. Also, the variance. The variance will be like it's 2n square, it's m plus n minus 2 and divided by m n minus 2 square n minus 4 for n is greater than 4. Okay, so this is the mean and variance. Okay, we will not discuss about its skewness and kurtosis that are like quite complicated. Okay, so these are the cases. Now we have some more properties related to this distribution. Let me write in the form of remarks or notes. So it is like, suppose if U follows F distribution with parameter Mn or with degree of freedom Mn. Okay, then 1 by U, the reverse of the reciprocal of the variable U. This again follows the same distribution F with the interchange degree of freedom, that is N. Okay, so U follows the F distribution with Mn degree of freedom, then 1 by U follows the same F distribution with Nm degree of freedom. So this is one case. Okay, also it's like if T, a random variable T follows a T distribution with N degree of freedom, then T square, this follows the same F distribution with parameter N and 1. Okay, so T square is a special case of F distribution for N equal to, sorry, for M equal to. Okay, also we have one more thing. Let me write here. Yes. So suppose X is a random variable which follows normal distribution with mean, mu, and variance sigma square. This last remark actually used many times when we perform any kind of numericals. Okay, suppose X is a random variable which follows normal distribution with mean, mu, and variance sigma square. Okay, then obviously we know that the Z, which is X minus mu upon sigma. Okay, this follows normal distribution with mean 0 and variance 1. That is the standard normal variate. Okay, now Z square, Z square is square of the standard normal variate, which is actually X minus mu by sigma whole square. This follows chi-square with 1 degree of freedom. Okay, so chi-square with 1 degree of freedom is nothing but the square of the standard normal variate. Okay, so hope up to this point everything is clear. If anyone have any doubt, please ask here. Then we have second topic here. Okay, we have second thing to discuss, and that is the descriptive statistics. Okay, as we have, as I told, like we will transfer, like we will discuss from ninth onward week about the statistics. So the basic of this is descriptive statistics. Okay, the same thing we need in this descriptive statistics, we need to like describe the data. Okay, and how to describe the data? And how to describe the data? Mainly we have four like characteristics that we need to calculate to describe a data. The first one is like measure of central tendency. The second one is like measure of dispersion. The third one is like measure of skewness, and the last is measure of kurtosis. Okay. We have already discussed these things actually many times, but not about the exact definition and all. So let me define here some definitions or some kind of things. Okay. So like in measure of central tendency, we need to calculate a central value. That means suppose we are given a data x1, x2, and xn. We need to find a representative of that whole data set. Okay, so that representative is known as central tendency. Okay, so that is usually like sample median, sorry, sample mean, sample median kind of thing. Mean, median, mod. These are like measure of central tendency. These are the characteristics which is used to measure the central tendency of a data set. Okay. Similarly, measure of dispersion is there. So, like dispersion is how a data set is scattered. This can be measured via measure of dispersion. So these characteristics like range, okay, then it's like variance, it's like mean deviation, about a point. Okay, so mean deviation is always calculated about a point, and that point either may any random point, any arbitrary point, or either a mean, or either median, or either any mod or any characteristic. Okay, so these can be measured via measure of dispersion technique. So the next is measure of skewness. We have discussed many times. So we can discuss about in skewness, we will discuss about the symmetricity. Okay, symmetricity of data can be discussed in this measure of skewness. Okay, and the measure of kurtosis is like the flatness or peakiness of a curve. It measures the flatness or peakness. Okay, a curve. Suppose we have a reference point that is the normal curve, and then if the next curve and another curve either is peaked as compared to that normal curve, so that is called leptokurtic. We have discussed in the above slide just, or the below one, that is the platyphotic. Okay, so these are the four things that describes the whole data, so called descriptive statistics. Okay, like you can take any example. Suppose we have 1 2 3 4 5. For example, let me write, just let's create some example randomly. Suppose we have 1 2 3 4 5. Okay, the mean value is 3, the median value is 3, the mod is not there because everything is equally likely and equally occurred. Okay, what about the this second example? Okay, let me write here something like that manner. The mean value is 3. Okay, so it's like 1 3 5. Again, the x bar is 3. Okay, but here it may possible, it may possible that this data, this distribution has different variance. Okay, or we can write here like this 0 3 and 6. So again, this distribution has 3 as mean, but its variance is different. Here, its range is like what? Range is x max minus x min. X max minus x min, which is 5 minus 1 comes out to be 4. Here, what is the range? 6 minus 0 comes out to be 6. So there, if we only calculate the measure of central tendency characteristic, that is a only mean are given to us, then we are not totally say about the whether the data is how dispersed, how scattered. Okay. In the same manner, we can draw any kind of curve. Okay, that way I'm just going to draw those 10. Okay. So these are the example. Like we have this kind of curve. Okay. So it may possible have the same peak, have the same ranges. It may possible but have different peaks values for different curves. Okay. So this implies yes, it the data set is different, but the mean value is same. The data set is different, but the range is same. Okay. So different kind of scenarios are there. So these are called the description. Now the next thing is let me write some formula actually. Like in description, in measure of central tendency, okay, we need mean. So there are various formula for means actually. Okay, so those are like the direct one, the obviously direct one. X bar is 1 by n summation xi. Okay, this is a direct formula. If we are given some frequency distribution, then again you can use like it's 1 by summation fi, summation fi xi. Okay, I from 1 to n or to those point. Okay. So these are given, these are the direct formula. These are when we are given the frequency distribution. Again, suppose we are having grouped distribution kind of thing. Okay, like 0 to 10, 10 to 20, 20 to 30 kind of data. Then in that scenario, we have two approach actually. Okay, we have two approach, that is either assumed mean method or step deviation method. So in assumed mean method, it is like assumed, we already assumed a number which is near to mean value, and that comes out to be like in the mid value. Okay. So it's a assumed value for the mean. Okay. This, and then it's like summation fi. It's like xi minus 2 divided by summation fi into x. Okay. Summation, just wait, yes. And then n fi xi minus 2. Okay. And in the same manner, this is the formula. In the same manner, suppose we have a large data, very big numbers data are involved in our calculation, then we have these are called assumed mean method actually. These are very basic formula already given in 10th or 12th class. Okay. Then we have one more formula, that is step deviation. When we are dealing with a very large number like data, then those these data is like it's 2 plus summation fi xi minus a upon h into h. Okay. So this here also I need to define is one more thing that I need to define. Suppose let me write here as 1 by capital N. Okay. So capital N is nothing but summation f, right? Okay. Because here it's like this. System is also there. Just give me a second actually. Hello. Sorry for the disruption. Am I audible?
Yes, sir.
Okay, thank you. Okay, so these are like xi minus a upon h. These are the difference. Okay, deviation. So this like simplify our calculation only, and nothing is everything is like same formula. Okay, so this is how we calculate the mean. Similarly, we have median. Okay, we have median. So obviously, median is that value of the observation that divides the whole data into two parts. Okay, so those two data is like those observation is like median one, median value. Okay, like 1, 2, 3, 4, 5. The median value is 3. Then the median value is 3. What if we have a grouped frequency distribution like 0 to 10, 10 to 20, 20 to 30 kind of? Then in that scenario, if we are given the class interval and then the frequency distribution, the frequency corresponding to the respective class, then first we need to calculate the cumulative frequency. Okay. And then the median value is defined as like L plus n by 2 minus C upon F into H. Okay. Here L is the median, like the lower limit of the median class. We have one numerical based on these. Okay. So I'm not writing all those things. So it is the lower value, lower limit of the median class, and the median class is defined from n by 2. Okay. Suppose we have n samples, n cumulative sum, n frequency. So n by 2 comes out to be a number. Then the median class is that class which cumulative frequency is just above the n by 2. Okay. Then from there, the L is the lower limit of that median class, n by 2, the value itself. C is the cumulative frequency just preceding the median class, just preceding the median class. F is the frequency of the median class, and H is the interval. Okay, like 0 to 10, 10 to 20 means H equal to 10, the interval width. So this is the grouped frequency formula to calculate the median. Similarly, we have mod. Okay, so mod has the same kind of formula. Okay, let me write here only. Okay, so mod has the same L plus its F1 minus F0 upon F1 minus F0 minus F2 into H. Okay, so this is the formula to calculate the mod. Here again, L is the lower limit of the model class, and the model class is defined as that class which has the highest frequency. Okay. The highest frequency is termed as the model class. Then the lower limit of that model class is L value. The next is F1, F0, and F2. Okay. So it may like it's F1, it's F2, it's F0. Okay. So this is our model class. Okay. So F1 is the frequency of the model class. Then F0 is the frequency just preceding the model class, and F2 is the frequency just succeeding the model class. Okay. So three successive classes. The middle one is the model class. F0, the preceding, the frequency of the preceding class. The F2 is the successive class frequency. Okay. So this is the how to calculate the mod when we are given grouped frequency data. Okay. We have one empirical relationship between the mean, median, and mod. Okay, that is like 3 median equal to 2 mean plus mod. Okay, so it's 3 median equal to 2 mean plus mod. This relationship is used when we are dealing with like slight kind of skewed data. When the data is highly skewed, then this relation not hold true. Okay, this only true when the data is either symmetric or slightly skewed. Okay, Now the next is symmetricity. Okay. So yes, you people have already seen many times. Okay. Suppose these three things. Okay. Here you can see, suppose this is the middle point. So the most of the data lie in the second half. So this is called the negatively skewed. Negatively skewed curve. Okay. In this curve, the mean value is actually less as compared to median value, and it is less as compared to mod value. So that is the mod value is the peak highest one in this scenario. Okay. Similarly, this is again kind of skewed data, skewed distribution. This is termed as positively skewed. And here the mean is greater than median and is greater than mod. So mean value is greater in all the cases. In case of positively skewed data. Okay, obviously we can also write like this. For negatively skewed, the beta 1 coefficient is less than 0. Actually, then it is negatively skewed. For positively skewed, beta 1 coefficient is greater than 0. Then the curve is positively skewed. The beta 1 is what? The measure of symmetricity. Okay, the measure of skewness, not symmetricity, the measure of skewness. And the third one, you can see it looks like normal curve, obviously. So it is neither positive nor negative, it's symmetric. And this is the point is called point of symmetricity. Okay. Here mean equals median equals mod. And here the coefficient of skewness comes out to be 0. Okay. So this is the skewness. The next and the last one is like kurtosis. So let me draw in the next page. Okay, sorry. Okay. So these are the cases. Here you can see there are three kind of curve possible on the base of their peakness or flatness. Okay. So let's assume this is the normal kind of. Okay. The reference point our is this. This is termed as mesocortic. Okay. The peaked one is kind of leptocortic, and the flat one is termed as platycortic. The plateau kind of. So that's less in height. Okay, so this one is flat one. The leptocortic one is the peaked one, and there is one, the normal one, which is the mesocortic. Okay, so obviously there are many scenarios possible in this as well. Like it, the leptocortic curve is either positively skewed or negatively skewed or symmetric in nature. Okay, as we have seen for the T distribution, the curve is symmetric but leptocortic in nature. Okay, so in the same manner, you may find the normal curve only. Okay, the normal curve is mesocortic and symmetric in nature. Okay, then the chi-square variant, that is like leptocortic and positively skewed. Okay, so different kind of scenarios is there. So we can use the central tendency, measure of dispersion, skewness, and kurtosis. With the help of these four, mainly four statistics, we are able to describe the whole data. Okay, so that's why it is called descriptive statistics, and we need to find these four to analyze the data completely or more inclusively. Okay, so anyone have any doubt up to this point? He or she may ask. So these are the topics that have already been covered in VK, but we have some snapshot. Now we can solve some numericals based on these topics. So anyone have any doubt? Please ask. Otherwise, we will solve some numericals from there onward. Okay. Okay, then let's solve some numericals. Now the first question is we are given a following frequency table actually. Okay. We need to calculate the mean, median, and mode, and then interpret from the following grouped frequency table. Calculate central tendencies and interpret the data nature. Okay, data's nature or data structure. Okay, so I'm going to write the table and then we will solve this together. The question we given the age group and the corresponding frequencies actually. Okay, so the age group is the age group is given like this. Age, so it's given here. Age group is like 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, 60 to 70, and 70 to 80. Okay, these age groups are given. Then we are given the frequency. The frequency is 30, 50, 54, 67, 59, 34, 39, and 30. So these information is given to us only. So now we need to find the measure of central tendencies. Okay, so that means we need to start with mean. Okay, for mean value, the formula is like we are given group frequency distribution. So the mean value is like what? X bar equal to summation Fi Xi times summation Fi. So here the summation Fi, that is the frequency sum. So you must calculate and find out. It comes out to be 377. Okay. But Fi into Xi. Here Xi is the class mark actually. And this is defined as that is actually midpoint of the upper and lower limit. Okay. So it's it's upper plus lower limit divided by 2. Okay. The mean value of this. It comes out to be 0 plus 10. 10 divided by 2 comes out to be 5. Xi will be like 5, 15, 25, 35, 35, 55, 65, and 75. Okay. So now Fi into Xi. So we need to write one more column for that. So Fi into Xi, 30 into 5 comes out to be 150, then 750, then 25 into, sorry, 25 into 54 comes out to be like, okay, I'm doing it in a wrong way actually. We can solve this or we can use some other formula. Okay. So yes, let me solve via some calculator. If you people have any calculator, you may solve because I don't have calculator here. Okay, see, we will solve like this. Okay. We have some numbers, then we can calculate the mean value. Okay. Now, what about the median? Let me start with median. Okay. So how to calculate the median first? The median can be calculated by, we will solve this. Okay. Now the median. Median is what? For median, we need, this is actually our Fi Xi column. Okay. We will solve this. Then we have median. And for median, our formula is like L plus n by 2 minus C upon F into H. Okay. So this is for our formula. Now here n equal to 377. So n by 2 comes out to be like what? 188.5. Okay. Now we need to calculate or make a table for the cumulative frequency, CF cumulative frequency. So it comes out to be 30, then 50, and plus above 30, it comes out to be 80, and then it's 134, then it's 201, it's 260, it's 308, it's 347, then it's 377. Okay, so this is the cumulative frequency. Now, for median, we need to define the median class, and the median class is that class whose cumulative frequency is just above this n by 2 value, which is 188.5. So it's 201. So that means what? That means this is our median class. Okay, so this is our median class. Now, according to this median class, our lower limit of the median class is 30 because here 30, 40 class interval, the lower limit of the class is 30. So the value of L comes out to be 30 plus n by 2. We have already calculated 188.5 minus C. C is the cumulative frequency just preceding the median class. So the cumulative frequency of the median class is 201 and the cumulative frequency just preceding the median class is 134. So that means what? 134 divided by the F. F is the frequency of the median class. So that is nothing but 67. 67 into H. H is actually 10 because we are given the class interval 10 to 20, 20 to 30, 30 to 40, and so on. So these are the cases. Now, the next is we need to calculate these things simply. Okay, so it comes out to be 30 plus it's 54.5 multiplied by 10 divided by 67. So it's 30 plus when you solve this, you may find it's approximately 8.13. So our median value is 38.13. Okay, we have calculated our median. I have just stopped to calculate the mean because the mean is quite laborious to solve here. Okay, we can use the class like the empirical relation here. Okay, or you can solve the mean first. There is no issue. Solve mean and median. Then using that empirical relation, you can solve mod. You can solve any two, and then third via that relationship. Okay. Now the next is median, sorry, mod. The next is mod. Again, the formula for the mod is L plus F1 minus F0 upon 2 F1 minus F0 minus F into. Okay. So now L is the model class. Now the model class is defined as the highest frequent class. So the highest frequent class is now again the same class, that is 30 to 40, because its frequency is 67, which is maximum in all the frequency. Okay. Our model class is 30 to 40. Now the lower limit is 30. The L value is 30 here. Plus F1. F1, that is the frequency of the model class. So that is actually 67. 67 minus F0 just preceding, F2 just succeeding. Okay. So 67, F0 is value is 54, and F2 value is 59. 54 and 59. Okay. So it's 54 and it's 59. Okay. F2 value is 59. It's 54. It's twice of F1. Twice of F1 is like 134. 2 into 67 comes out to be 134 into H. Let me write the value of H here as well. These are just simple calculation. Okay. These are just calculation. You need to know the formula and then the interpretation, what you got as a result. So mod is 30 plus 67 minus 54 divided by 2 into 30, 67, that is 134 minus 54 minus 59 into 10. Okay. So this comes out to be like it's 30 plus, yes, it's 13 upon, let's solve this actually already. So it's like 21 into 10. This is 30 plus 130 upon 21, which is 30 plus comes out to be 6.1. Okay. So our mod is equal to 36.19. Okay. Now you can solve median via summation xi or using some assumed mean method or some any method. So I am using here, since 3 median equal to 2 mean plus mod. This is the empirical relation. Okay. So I'm going to use this. 3 into the median value is like 38.13. 38.13 equal to 2 into mean. The mod value is 36.19. So 38 into 3 comes out to be like 114.39 equal to 2 into mean plus 36.19. So mean is like what? Mean is 78.2, 114.39 minus 36.19. So 78.2 divided by 2. So the mean term will be 39.1. Here you can see like mean is this, median is like 38.13, and mod is like 36.19. So you may find the mean is greater than median, and this is greater than mod. So what this implies? This implies this data structure that are given, this data, this data structure is actually positively skewed. Not very much, but slightly positively skewed. So this implies positively skewed data structure. Okay, so this is how you may find. This is only the central tendency. You can now find the measure of dispersion, then skewness, then kurtosis. Okay, but yes, you have more or less kind of concept that when you calculate the skewness, you will definitely find the positive value of beta 1. And that is from here we can observe mean is greater than median and greater than norm. Okay, so this is the case for the positively skewed data. So yes, we can directly say, we not rigidly say, but we can interpret as positively skewed data. Okay, so any doubt up to this point? No. So let's solve some more numericals. The next question is the mean marks in subject A. The mean marks in subject A, suppose there is subject A statistics of 50 students in a class were 36. Okay. Now the mean marks of boys was 38. The mean marks of boys was 38 and their number is 28. And the number of boys is 28 in the class. Okay. Find the mean marks of girls. Find the mean marks of girls students. Okay. So we are given a class of 50 students. We are given a total. So N is stand for total. So total students is 50. NB is stand for number of boys. So number of boys is 28. So obviously the number of girls is total minus number of boys, which is 50 minus 28 comes out to be 22. Okay. Now the average class average, that is, let me write X bar. So X bar is like 36. Now the average for the boys is 38. We need to find the average for girls. So that is not found. So it is a combined mean problem. So we are given a portion, okay, and we are given a total, and we need to find the another section combined mean. Okay. So we have a formula actually. Direct we have a formula. The combined mean X bar is N1 X1 bar plus N2 X2 bar plus Nk Xk bar. Suppose we are N section or N categories, then it's N1 plus N2 plus Nk. This is the combined mean formula. So yes, we are given X bar here. Let me write the formula directly. X bar is here 36 equal to N1 X1 bar. So we replace with NB and NG. So it's NB is 28 into XB bar is 38. Thus NG is 22 plus its XG bar, because we do not know the value of XG bar, divided by NB plus NG. Obviously it comes out to be 50. Now simple, we need to simplify this. It's 36 multiplied by 50 minus It's 28 multiplied by 38 equal to 22 xt bar. So here xt bar comes out to be like it's 1800 minus its the simple calculation 28 into 38 comes out to be like what it comes out to be 106864, sorry, 1064, and then divided by 22. So it comes out to be like 736.22. So xt bar is like 33.45. Okay, so we are given the average of one section and the whole average. We need to find the average for the another section. So this can be solved via combined mean. This is the combined mean formula. Okay, and the average for girls is 33.45 marks. Okay. Now the next question is like simple question actually. This is actually a property. Suppose x, y, and z are three independent chi-square random variable. X, y, and z are three independent chi-square random variables with 1, 4, and 9 degrees of freedom, respectively. Okay. Now find the distribution of S, which is x plus y plus z. Okay. These are just based on property actually. So this is the additive property actually. Additive property of chi-square variable. That is what if x1 chi-square n1, x2 follows chi-square n2, and xk follows chi-square nk. Okay. Then and xi's are independent. Then summation xi follows chi-square distribution. If these are chi-square and are independent in nature, then summation xi follows chi-square with summation ni degree of freedom. Okay. Summation run from 1 to k. Okay. So this is the case. So we are given the same case for 3. So yes, here s, which is equal to x plus y plus z. This follows chi-square variate with 1 plus 4 plus 9 degree of freedom as given here. 1 plus 4 plus 9. So that means S follows chi-square with 14 degree of freedom. That's simple. Okay. You can now calculate the expected value of S, which is 14. The variance of x is S is 28 because it's 2 into 20, 14, that comes out to be 28, and so on. Okay. Now, the next question. Any doubt up to this point? Anyone? We are given a question like the mean, and standard deviation of 10 observation are given to be 5 and 3. Okay. If every observation is multiplied by 2, if every observation is multiplied by 2, then what is the mean and variance of the new series? What is the mean and standard deviation what is the mean and variance of the new series, or mean and standard deviation of the new series? Okay, simple question. So let's start solving. You people may solve by yourself as well. Okay. Now we are given mean and standard deviation of 10 observation are given to be this. So we are given like n equal to 10. The mean value is like x bar, which is comes out to be 5. And the standard deviation, let me write s, and it is 3. The variance is obviously 3 square, that comes out to be 9. Okay. Now every observation is multiplied by 2. So yes, let's start. We are given x bar equal to summation xi upon n. Okay. Now here summation xi is 5. Summation xi, I from 1 to 10 obviously. And then n is 10 because. Now from here summation xi comes out to be 50. If you may find, you may find summation xi is 5 into 10, that comes out to be 50. Okay. Now that means what? That means x1 plus x2 plus x10 equal to 50. Now our question says if every observation is multiplied by 2. So this means what? So as the question says, it's 2x1 plus 2x2 plus 2x10 multiplied by 2. Okay. So we need to find this. So we can take 2 as common. So it's again x1 plus x2 plus x10. And yes, this value comes out to be 50. So it's 2 into 50. So the new summation xi comes out to be like 100. Okay. The new summation xi comes out to be 100. Now, the x bar, the new x bar is like what? New summation xi upon n, because n is still the same, the 10. So it comes out to be 100 upon 10. So the new mean is 10. Now the next is variance or standard deviation. Since sigma square is like 1 by n summation xi square minus x bar whole square. I need to write in capital letters like capital Xi, but I'm writing currently this, so let me write this for homogeneity purpose. So it's 1 by n summation xi square minus x bar square. Okay. So now it's we are given sigma square. Okay. The value of sigma is 3 actually. Yes. Value of sigma is 3. The mean is 5 multiplied by 2. Okay. So obviously 3 square comes out to be 9. So it's 1 by 10 and it is summation xi square minus x bar square. So the old, because we are discussing about the old one now. So the old data, from the old data, x bar is actually 5. So it's 5 square. Okay. So it's 9 plus 5 square is 25 upon 1 by 10 summation xi square. So from here, summation xi square comes out to be, it's 25 plus 9, it's 34. 34 into 10, it's 340. Okay. Now, that means what? That means x1 square plus x2 square plus x10 square comes out to be 340. Now, we multiply each observation by 2. So that means 2x1 whole square comes out to be 4 into x1 square. Okay. 4, or it is like 2x1 square plus 2x2 square and plus 2x10 square. Don't need to write this. I need to find that. So obviously 4 is taken as common. 4x1 square plus 4x2 square. So it's 4. It's x1 square plus x2 square plus x10 square. So yes, this value comes out to be 340. So it's 4 into 340, which is what? The new summation xi square is actually 1360. Okay. Now we have the 13 into 60. So the new sigma square, that is the new variance, is like what? It's 1 by 10 into 1360 minus the new mean, that is 10, 10 square. So obviously it's 136 minus 100. So new sigma square is 36. So new sigma is under root 36, comes out to be 6. Okay. So the new mean is 10 and the new variance is 6. 6. New standard deviation is 6. So yes, we have a formula actually. People have remembered the formula, right? It is like expectation of AX is equal to A into expectation of X. Okay. So that means when we perform multiplication of 2 with all the data, so the same case has apply on the expected value as well. So our initial mean value is 5. Initial mean value is 5. And then we multiply each observation by 2. So this implies our new mean becomes 2 into 5 comes out to be 10. Now the next thing is variance. Variance of AX is equal to A square variance of X. And then standard deviation of X of AX equal to A into standard deviation of. Okay. So the standard deviation also follows the same trend as the mean. So it comes out to be the initial or the initial standard deviation is 3. We multiply each observation by 2. So 2 into 3 comes out to be 6. Okay. So this is the case. Any doubt up to this point? Okay. So now the next question. The question is like, we are given the following data. We are given the following data. Suppose we are the data A is like 10, 20, 30, 40, and 50. And data set B is like 5, 15, 25, 35, 45. Okay. Now we are given like some options here. Like the first one is CV of A is greater than CV of B. That is coefficient of variation. Coefficient of variation of data set A is greater as compared to that of B. The second option is like CV of A is less than CV of B. The third option is like X bar of A is greater than X bar of B. And the last is X bar of that's average, the sample mean A is less than X bar of. Okay. So this is the case. We need to find which observation or which two or which three observation is correct. So yes, CV is stand for coefficients of variation. And its formula is like HD by mean. Sometimes people write it 100 for the percentage case or HD by mean as a probability case or ratio case, or probability ratio case. Okay, so let's solve this. The data set A is given 10, 20, 30, 40, 50. So obviously, the first thing is X bar, which is summation Xi by N. So XA bar is like what? 10 plus 20 plus 30 plus 40 plus 50. So it's 10 plus 20 plus 30 plus 40 plus 50 divided by 5 comes out to be 30. Similarly, XB bar is like 5 plus 15 plus 25 plus 35 plus 45 divided by 5 comes out to be 25. Okay. So now the coefficient for the coefficient of variation, we need standard deviation. And the standard deviation formula is like what? 1 by n summation xi minus x bar whole square under root. Okay. So SA for data set A, it comes out to be like what? Since we are 5 data, I'm not going to construct the table for all, just starting here directly. So x1 minus x bar. So the x1 is like the first value, that is 10, the 10 here, minus 30, 20 minus 30, 30 minus 30, so on. 10 minus 30 whole square plus 20 minus 30 whole square plus 30 minus 30 whole square plus 40 minus 30 whole square plus 50 minus 30 whole square. So this is the standard deviation for the SA. Obviously, you may find it's 1 by 5 into its 400 plus 100 plus 0 plus 100 plus 400. And it comes out to be like under root 200. That is 1000 divided by 5 comes out to be under root 200. So standard deviation for the data set A is actually 14.14. Approximate value is 14.14. Now the next, similarly, SB is also there. You can directly write the same thing. Okay, using the same thing, you may find the same value for this as well. Okay, I'm not going to solve this. The same structure is there, only the numbers are different. Okay. Now coefficient of variation for A is SA upon XA bar. So SA will be like 14 upon 14.14 divided by X bar is like 30. XA bar is 30. So its approximate value is 0.47. Similarly, coefficient of variation for the data set B is SB upon XB bar. It's 14.14 divided by 25. The approximate value 0.566. So yes, from here you may find X bar A is greater than X bar B and CVA is less than CV of. So that means what? So this one and this CVA is greater. No, CVB is greater. Sorry, the coefficient of variation B is greater. So option second and option third is the correct one. Okay. Is it okay up to this point? I have some more questions as well. Some questions related to TF and chi-square, obviously. So the question is like, let x1, x2, not xn, x3, and x3. These follows the normal curve, normal distribution with mean 0 and variance sigma square. And these are independent in nature. Now define the Q transformation x1 is square plus x2 is square plus x3 is square divided by sigma square. The first we need to find is distribution of Q. The second thing is we need to calculate the expected value of Q and variance of Q. Here xi's are independent is also given. Okay, so we need to find the distribution of the transformed random variable Q, which is defined as the x1 square plus x2 square plus x3 square divided by sigma square, and then the mean and variance of that distribution. Okay. So here we are given xi follows normal 0 sigma square for all I 1, 2, and 3. Okay. So in this case, always use the standardization of the normal variate. So what is Zi? Zi is xi minus mu. So that is 0. So let me write xi directly divided by sigma square. Okay. And this follows normal 0, 1. Now, as we know that Q can be written like x1 square plus x2 square plus x3 square. Okay. It's x1 square upon sigma 1 square, x2 square upon sigma 2 square. Let me write here x1 square upon sigma 1 square. Okay, not sigma 1, it's sigma only because all sigmas are equal, plus x2 square upon sigma square plus x3 square upon sigma square. Okay, so this is given. Also we know that Zi is not Zi, let me write Z or Zi square can also be written. It's chi-square with 1 degree of freedom. This is the remark actually. Okay. The square of the standard normal variate follows the chi-square distribution with 1 degree of freedom. Okay. So yes, you can see and now find out Q is here. Here the Q, which is summation of Zi square I from 1 to 3 follows chi square plus 1 plus 1 plus 1, 3 degree of freedom. Okay. So Q follows the chi-square distribution with 3 degree of freedom. Now, the second question is like expectation of Q. Obviously, it's the degree of freedom itself, which is 3. And the variance of Q, it's twice of the degree of freedom, which is the simple question. If you know the formula, then or the property, you may solve the question directly. Okay. Is this any problem up to this point? Okay. We have same question, similar kind of question again. Okay. So like here we are given x1 follows normal 0, 1 and x2 follows normal 0, 1. Okay. Now we have a transformed distribution, transformed random variable y, which is x1 plus x2 whole square divided by 2. Okay. X1 plus x2 whole square, not x1 square plus x2 square divided something. It's x1 plus x2 whole square divided by 2. Now we need to find the distribution of y. Okay, the same question actually. Now you need to recall the property of normal distribution. Okay, here we are given x1, x2 follows the normal distribution with parameter 0 and 1. Okay, with mean 0 and variance 1, obviously. Okay, we may recall that the linearity property of normal distribution as the linearity property of the normal distribution. And what it says if x1 and x2 and x3 and xk are linear, are following the normal distribution, then their summation will also follow the normal distribution with the mean is summation of the individual mean and the variance is the summation of their individual variance. Okay, so this is the case. I'm not writing these things. I'm just saying and writing the direct form. So from here, what? From here, x1 plus x2 follows again the normal distribution with mean x1 follows 0, x2 follows 0, then x1 plus x2 follows 0 plus 0 comes out to be 2, 0. Not 2, 0, obviously it's 0. Then the next is variance. Variance is what? 2, because it's 1 plus 1 comes out to be 2. So x1 plus x2 follows 2. Normal 0, 2. Okay. Now, this is the linearity property. Now the next is standardization, because now we have a normal distribution with some mean and variance. Now standardization. So what is standardization? Z, which is x1 plus x2 minus 0. So I'm not going to write minus 0. Divided by the variance is 2. So the standard deviation is root 2. Okay. So this follows normal 0, 1. Okay. Now z square is what? X1 plus x2 whole square divided by 2. This is what? This is nothing but this y only. Na? X1 plus x2 whole square divided by 2. So this is y actually. So obviously this follows chi-square distribution with 1 degree of freedom, because x1 plus x2 whole square divided by 2 is normally distributed. X1 plus x2 divided by under root 2 is normally distributed with mean 0 and variance 1, that is the standard normal variate. So the square of that standard normal variate comes out to be the chi-square distributed random variable with with degree of freedom. Okay. Is it okay up to this point? Okay, now we have some more questions related to t distribution. So solve this question as well. Now the question is, let x1 and x2 follows normal 0, 1. The same question actually. Okay. Let x1, x2 follows normal distribution with mean 0 and variance 1. And we have another random variable u which follows the chi-square distribution with 2 degree of freedom. Okay. And these are independent. Okay. Now find the distribution of the random variable t, which is defined as the x1 plus x2 divided by under root of u. Okay, x1 plus x2 divided by under root of u. So again, let's start. Same thing. Since x1 plus x2, sorry, x1 and x2 follows normal distribution with mean 0 and variance 1. Then x1 plus x2 follows the normal distribution with mean 0 and variance 2. So from here, the z, which is x1 plus x2 divided minus 0, that is nothing, divided by under root of 2 follows normal distribution with mean 0 and variance 1. Okay, now we are given, since we are given t is x1 plus x2 divided by root u. So x1 plus x2 from the above, x1 plus x2 is nothing but root 2z. Okay, so it's root 2z divided by root u. Okay, so now it's z divided by under root of u by 2. We can write like this. Okay, root 2 and root u. So whole under root of u by 2. So here what? The upper term is normal. Okay, like here you can see, we know that z, the numerator term is standard normal variant and the denominator term is chi-square variate with some m degree of freedom and divided by the same its m degree of freedom, then in that case it follows t with m degree of freedom. So using the same formula, we can compare the u value, u is chi-square variate with 2 degree of freedom. Okay, so this implies what? T, which is x1 plus x2 divided by root u, it follows not chi, it's t, t degree of t with 2 degree of freedom. Here x1 plus x2 divided by under root u as follows, t distribution with 2 degree of freedom. Okay, just simple comparison, just the definition of how the t variate is formed. Okay. In the same manner, we have some numericals based on F distribution. So let me write one or two more question. Just this is actually just the definition. So suppose we are given u, okay, which is equal to x1 square plus x2 square. We are also given v, which is equal to x3 square plus x4 square plus x5 square. Also, here xi follows normal distribution with mean 0 and variance 1 for all I to 5. Okay. Now find the sorry. Find the distribution of it's u by 2 divided by v by 3. Okay. So again, since xi follows normal 0, 1. So this means xi square follows chi square 1 and summation xi square follows summation chi square. And here I from like 1 to n, so it's n degree of freedom. This is the property. So u, which is equal to x1 square plus x2 square. This follows chi square variate with 2 degree of freedom. Similarly, v, which is x3 square plus x4 square plus x5 square, chi-square variable. 3 degree of freedom. Now, uh, the thing that we have defined like u by 2, it's u by 3. This is nothing but chi-square variable with 2 degree of freedom divided by 2, chi-square variable 3 degree of freedom divided by 3. So this is what? This is the definition for the F variate with 2 and 3 degree of freedom. The numerator 1, 2, and then the denominator 1, 3. Okay. So this is the case. Now we have 2 or 3 more questions. The simple one. Let me write quickly. We are given a data set A as we are given data set A has the mean value 50 and the standard deviation is 5. Okay. And the data set B is formed from y equal to 2x plus 10. Okay. The data set A has the mean value 50 and the standard deviation 5. The data set B, which is formed from the data set A by y equal to 2x plus 10. Now we need to compare the coefficient of variation. Compare the coefficient of variation. Okay. So CV, that is CV. Okay. So yes, for the CV, the coefficient of variation and all. So let me first, if y equal to ax plus b kind of transformation is there, then in that scenario, expectation of y, remember a into expectation of x plus b, and variance of y is a square variance of x, and standard deviation of y is a into standard deviation of x. Okay, so this is the case. They've already repeated many times. So from here, x bar is 50 and s, which is standard deviation, is 5. So y bar is what? Y bar is it's 2x, no? 2x plus 10. So it's 2 into x bar plus 10 comes out to be 110. And standard deviation of y bar is like 2 into 5 comes out to be 12. Okay. So yes, now the coefficient of variation for the data set A is what? SD by mean. So SD will be 5, by mean is 50, comes out to be 0.1. Now the coefficient of variation for the data set B is SY upon RY, or not X R Y, let me write it Y by directly. So it's like 10 divided by y bar is 110. So obviously it's 0.1, it's less than 0.1, which is 0.091. Okay. So from here we can see the coefficient of variation of A is greater as compared to the coefficient of variation of B. So that means what? The data set A has more variability in the data as compared to the data set B, which is a transform from the data set A. Okay. So we have a similar kind of question. Suppose we are given two data set with same mean, sorry, same variance and different mean. Okay. just a logical kind of question. This is okay. We are given two data sets have same variance. We are given two data sets have same variance. Okay, but different means. After combining, the question is after combining, will variance increase or decrease? Okay, so we have already solved one question based on the combined mean. Now this is for combined variance actually. Okay, so this can be solved by either assuming any example or direct in a general form. So I'm trying to solve this in a general form. So let the data set 1, okay, or the data set A. So the data set 1 has n1 number of sample, its average value, the mean value or sample mean is x1 bar, and its variance is sigma 1 square. But here we are given the same variance. Okay, we are given the same variance, so I'm considering sigma square. Okay, the same for the data set 2, the n2, x2 bar, and sigma square. Okay, now you may remember combined mean formula, which is x bar, which is n1 x1 bar plus n2 x2 bar and divided by n1 plus n2. Okay, so this is the formula. Okay, now we have combined variance formula as well. Okay, so combined variance. So let me write by sigma c square, which is n1 sigma 1 square plus x1 bar minus x bar whole square. Okay, and the same it's n2 sigma 2 square plus x2 bar minus x bar whole square whole divided by n1 plus n2. This is only for two data sets. Okay. Now, what we are given here, the sigma 1 square equal to sigma 2 square equal to sigma square say. We are given this condition. So in that scenario, sigma c square is what? N1 sigma square plus s x1 bar minus x bar whole square plus n2 sigma square plus x2 bar minus x bar whole square whole divided by n1 plus n2. Now we can like reshuffle these terms and then we can find n1 sigma square, n2 sigma square. So it's n1 plus n2 sigma square divided by n1 plus n2 plus we have n1 x1 bar minus x bar whole square plus n2 x2 bar minus x bar whole square whole divided by n1 plus n2 sigma c square. Okay, I hope up to this point everything looks fine. Now see, here this value comes out to be what? Sigma c square is equal to what? Sigma square plus some extra term. Okay, so this extra term n1 x1 bar x bar whole square plus n2 x2 bar minus x bar whole square whole divided by n1 plus n2. So here x1 bar minus x bar always comes out to be positive, and the same for the x2 bar minus x bar. So overall this term is positive. Okay. So this implies what? The combined variance is greater for the what the question is? The question is yes, the fold variance or the individual variance. Okay. Okay. The old variance is like sigma square, but here sigma c square is greater as compared to the old variance sigma. So is it okay up to this point? Any doubt? Okay, the last question. We are given mean of 200 observations. Mean of 200 observation is 30. Later it was found that later it was found that 25 and 35 were 25 and 35 were wrongly recorded instead of 20 and 15. Okay. Now find the correct mean. Okay. So this is a simple question again. Suppose we are given 200 observations. So that means what? N equal to 200 is there. Now it was given the mean is 30. So the mean value, let me write x bar is 30. Later it was found that 25 and 35 were wrongly recorded instead of this. Okay. So obviously, again, the same case, we know x bar equal to what? Summation xi upon n or summation fi, whatever is there. So here, from here, what? From here, summation xi equal to nx bar actually. Okay. So summation xi equal to 200 into 30. So this comes out to be summation xi equal to actually 6,000. Okay. So this is the case when we are dealing with the wrong data. Okay. Or misprint or typo data. Okay. Now, instead of using 25 and 35, 25 and 35, we need to write 20 and 50. Okay. So that means what? So the new summation xi. New summation xi is log what? 6,000 minus the 25 and 35 will be minus. So 25 plus 35. Then add 20 plus 15. Okay. So it comes out to be 5,975. Now the corrected mean will be like new summation xi upon n. So the new summation xi is like 5,975. It's 200. And yes, x bar corrected is actually 29.875. This is the approximate value. Okay. a simple type of question. These kind of question are usually asked in the examination or in the assignment as well. Okay, so these are the cases. Actually, there is one general formula. If you want, you can write like the corrected mean is equal to actually nx bar, which is the summation xi, okay, minus the wrong values, okay, and then plus the correct values, and then whole is divided by n, okay? Minus the wrong values plus the corrected value, whole divided by n. This is the corrected mean formula, the direct formula actually. Okay. So these are the cases. If anyone have any question, any doubt, you people may ask. If not, I think we can conclude our session here. Anyone?
No, sir.
Okay. Okay, thank you. So if there is no question, we can conclude our session here. Thank you, everyone. Let me first stop the recording.